the keynote, and thank you for attending the workshop, the embedded SIGCOMM tutorial on machine learning in network machine learning with Taurus. My name's Kunle Olukotun, and I'm a professor at Stanford. Been there for many years, and my main area is computer architecture. And Shabazz, who you know well, is responsible for me being here and being in, playing in the networking community, which is something that I hadn't done until I met Shabazz. I'm also a co-founder of a company called Sambonova Systems, and Sambonova is a company that develops systems for ML, including hardware and lots of layers of software on top of that. And I'll mention how Sambonova plays into what I'm going to talk about today. So the title of the talk is Machine Learning and Systems, a Virtuous Cycle. And so what I want to talk about is the interplay between systems and ML, or ML and systems, and how the two reinforce each other to build more interesting, more capable computer systems. So let me start by talking about, ideas that you already are fairly familiar with. The two big trends in computing. The first, of course, is Moore's law is slowing down, right? Some people say it's dead, others say it's just resting. But the fact of the matter is that the time between generations is increasing, and if you're Intel, you might have, you might say it's increasing much longer than you might like, and the cost per transistor certainly isn't dropping the way that it used to when we think about Moore's law. I think, more importantly, from a systems point of view, well, of course, cost is really important. But the other thing, of course, is the companion law to Moore's law, which is Dennard scaling, right? Which says, that as we scale to small transistors, the power, goes down. So that as we increase the number of transistors, we double the number of transistors, we keep the power constant. Well, that has been gone for a while now, and so fundamentally all of computing is power limited, and which means inefficient ways of building processors such as general purpose CPUs no longer scale. The other big trend, of course, is the overwhelming success that machine learning is having in all sorts of areas, right? It's transforming the way that we develop applications and software. It's really big in terms of sort of attacking tasks that we traditionally had trouble doing with previous algorithms, such as image recognition and natural language processing. And these sorts of things, of course, are having societal scale impact as it's transforming the way we do autonomous driving. It's changing the way we do research in medical and other scientific domains. And of course, it's changing the way that we develop medical innovations from drugs to personalized medicine. And so if you look at machine learning, of course, there's an insatiable demand for computing, both in training very capable and accurate models and also for serving these models potentially to millions of users. And so the very time that we have this fundamental limits that are faced in the way that we improve computation, we need ever more computation to develop new machine learning models. So this virtuous cycle then between machine learning and systems, of course, is the idea that machine learning is something that you want to continue to improve, both training and inference, and then you can do that not with general purpose computation, but with more specialized systems that are focused on solving the sorts of computational problems posed by ML. And of course, by doing this, you are enabling the development of more and more accurate ML models, which allow you to apply these models to a wider variety of different applications. In particular, you might think about applications that improve the systems that you're building that you're developing to run your ML problems on, right? And so you can think about how these systems then are being enabled or improved by ML, right? So you had systems that you were building to improve ML, then you also have ML being used to develop better systems, which of course leads to more machine learning, and the cycle continues. So this talk is going to be in two parts. First, we want to look at sort of building systems for ML, and that will probably be the majority of the talk. And then the latter half of the talk will be how we develop better systems using ML. So let's start by talking about systems for ML, right? Developing better systems for ML. And so ultimately, of course, what we want to do is develop these systems in the context of the Moore's law slowdown, right? And so we want to continue to improve our capabilities to do the sorts of computation that underpins ML. And so let's suppose we want to improve, training and inference by 100 times. Moore's law slowdown says that, we're fundamentally power limited. And so this means that, of course, improving performance has to mean improving power efficiency, energy efficiency, performance per watt. And so one way, of course, to do this is to make a system that's very specialized ASIC for a particular ML algorithm. But of course, ML is not a static algorithm. What happens is that there's innovation in the models that people are developing. And so you want programmability at the same time that you want very high efficiency. So ideally, of course, you'd like the efficiency of a specialized ASIC, but of course that's not programmable. And so you also want the flexibility of a CPU, which we fundamentally just said that that's not efficient. So you need some way out of this conundrum. And the way out is to take a full stack approach to design of these systems, right? One that looks at what direction the ML algorithms are moving in and understands what kinds of characteristics one needs to focus on in improving performance. And then, one of the key things that you'll notice from looking at these sorts of algorithms is that data flow plays a major part in the computational paradigm. So thinking about how to develop data flow abstractions and optimize them is going to be a key component of the solution. And then specialized hardware focused on data flow. And so this notion of data flow is pretty general. And so this gives you the flexibility that you need to allow innovation in ML algorithms. So let's start by looking at these three components of the full stack integrated solution to improving ML. So let's first start by looking at ML algorithms. I think the big trend in ML algorithms, if you talk to ML practitioners these days, is the emergence of these very large, autoregressive, self-supervised models called foundation models. At Stanford, there's a new lab called the Center of Research for Foundation Models. And these models are trained on huge amounts of data, right? So the examples might be GPT-3 as a natural language model, or DALL-E as a sort of image generation model. And the nice thing about these models is that in the past in machine learning, one had to develop a new model for every task that you wanted to attack. And with these new models, they have in-context learning, in that you can train the model on a huge amount of data, and then you can use in-context learning to specialize or to specialize the model for a particular task, right? So, and this allows you to do amazing things, right? You can build apps that used to take, days or weeks in a matter of hours, right? You don't need a specialized model for every different thing that you want to do. And so, these models are already very capable. You think about what you can do with GPT-3 or DALL-E 2. So DALL-E 2, of course, is this image generation model. So here's an example of an astronaut riding a horse, right, which was generated just by saying just that, give me an astronaut that's riding a horse, and that's what you get. So it's fairly impressive. And these foundation models allow you to do incredible things in terms of what they can do with text and images. And as I said, that they're self-supervised training. So here's an example of sort of emergent behavior. Suppose I want to, the input that I want is the get the capital from country, right? And so you might give it a few examples: France and Paris, Germany and Berlin, Japan and Tokyo, and then say, okay, well, what about Canada? And GPT-3 will say Ottawa. It doesn't always get it right. Sometimes you might get Toronto, but most of the time, you get the right answer. And this is just one example where all you needed for the prompt was, a few sets of input text, and you get the output. Also works for translation, works for questioning and answering, and can do arithmetic and all sorts of things, right? So, and then over time, these models are becoming more capable as the number of parameters and the size of these models increases. And of course, everybody who has the capability is focusing on these models. So Google, of course, OpenAI, Meta, they all have projects. And so, GPT-3 is 175 billion parameters. And then there are more recent models with much larger numbers of parameters that are potentially more capable. But of course, actually building these models is incredibly difficult, right? So the Center for Foundation Models at Stanford, came up with this very detailed report. And, one of the conclusions is that, you see the quote here, that one of the largest bottlenecks to building these models is they are huge, right? So they don't fit in the memory of most GPUs, at least, so you need tens or hundreds of GPUs to just hold the models. And of course, you also need a large number of GPUs for the compute capability required for these models. So 100,000 petaflops per day for GPT-3, and hundreds of thousands of dollars of computing capability over months. And then, of course, once you've got the model and you want to fine train it for a specific task say in business or finance or medicine, that can take more computation. And so training these models, as I said, GPT-3 takes 1,024 GPUs and months of computation. And over time, if you look at the efficiency with which these GPUs are being used, it gets smaller. The efficiency goes down as you scale the number of GPUs that you need to do the computation. And so if you kind of look over time at how fast the size of the parameter growth, it's like it's doubling every 2.5 months, right? So way outstripping Moore's law. And so clearly, just by using brute force and increasing the number of parameters at this rate, we're going to run into a wall. So, so what do you think that you might want to do? You might want to think about how you have a large number of parameters, but don't train the model in a sparse manner, right? And so that's the idea of sparse training for neural networks, right? And so the key to sparsity, do you have a question?
We could give a sense of our consumption of this. I heard that every time you run GPT-3, you need to burn a forest.
Well, I think some of the. Do you want to wait till you want to do it in line?
Yeah, at the end of
When we hold the questions to the end, I'd be glad to answer that question. It's a very good question, but let's hold it to the end. Okay, so. So one of the approaches then would be sparsity, right? And so the question with sparsity is, how do you get a model that is both accurate when you train it using sparsity, but also more importantly, or just as importantly, how do you make sure that you use the compute acceleration capability efficiently, right? So sparsity fundamentally is a much more difficult computation problem because it tends, in fact, to be more memory bandwidth limited than dense computation, right? Dense computation is nice. As you know, as you may know, most of these algorithms, machine learning algorithms, are dominated by by matrix multiply, right? So dense matrix multiply, as we know, for n squared data, you do n cubed computation, right? Which is great from a compute to memory access ratio, an efficient operational intensity capability. So what happens when you do sparsity, of course, is that you are decreasing the number of operations, the number of flops you need to train and infer the model, but you are also decreasing the amount of data that you need, right? And so the challenge then is, can you get accuracy and hardware efficiency? And so recent work by Chen and Dao out of Chris Ray's lab shows that, with these ideas of pixel butterflies, where you are using block sparsity, you can both get accurate models at the end, just as accurate as you had with the dense training, but also you can use the GPU efficiently in doing the computation, right? If you just think about random sparsity, that doesn't work well on GPUs at all. And you may, in fact, have trouble getting the accuracy you need. But with the structured sparsity, this block sparsity, you can achieve that. So that's one thing to keep in mind. Sparsity is going to become more and more important. The other thing to keep in mind about these models is that fundamentally data flow, right? So you think about machine learning models, they are described as a graph of kernels, right? Such as matrix multiply, convolution, pooling, normalization, and the such. And these kernels, of course, are connected by tensor data that moves from one kernel to the next. And the models, of course, are described using high-level domain-specific languages for machine learning, such as PyTorch and TensorFlow. TensorFlow was one of the earlier ones. In fact, the earliest language for machine learning, which of course didn't become hugely popular, was one that was developed in my lab. It was called Optimal, right? OPTIML, right? Spelled that way and pronounced optimal. And so it predated all of these ideas. And in fact, it was precursor. It was it showed the way, sort of how to develop a domain-specific language that is both, very productive in terms of being able to develop applications using it, but also is very high performance. And so that was the goal of the work. All right, so what implications do we get from the algorithm by looking at the algorithms? Clearly we want to be able to train these very large models, right? And so we've got to think about how we do it as energy efficiently as possible. The models are huge. These foundation models are billions of parameters, right? So you need very, very large models, terabyte-sized models, in order to get the state-of-the-art accuracy. Clearly, in order to train these models going forward, we need to be smarter, right? So sparsity is something that we need to take advantage of, especially block sparsity, so that we can get good compute efficiency. And then lastly, data flow graphs, fundamental to the way in which these algorithms are described. And so exploiting that characteristic of these models will be important. Right, so thinking about data flow then, let's think about data flow compilers, right? So one of the things that I've worked on over the years, I started out thinking about computer architecture, but very soon figured out that, hey, you also needed to write software to run on these weird computer architectures, parallel architectures initially, and more strange architectures or more recently. And so that leads you into thinking about, compilation approaches. And so we worked on, as I said, this idea of domain-specific languages. We were very early on. We said, the way forward here is not to take a general purpose language like C and try and extract huge amounts of parallelism from it. It's too difficult. People have been trying to do this for 50 years. What you want to do is specialize the language for a particular task and raise a level of abstraction, and then think about how you extract performance from these high level of abstractions, which is exactly what these ML languages do, right? And so you can think about this data flow graph of operations that come from languages like PyTorch and TensorFlow. And then what we realize is that, hey, if you think about these different languages, you can describe the domain-specific data flow represented by the operations like convolution and pooling and so on in a lower level, more generic parallel in representation that we call hierarchical parallel patterns, right? So parallel patterns, which you are probably familiar with, like map, reduce, group by, and filter. And it's important that they be hierarchical, right? Just flat map reduce won't do it in terms of their expressive power for representing these graphs. You want something that is hierarchical. And so, you can do ML, dense and sparse linear algebra, but you can also do relational algebra, right? So if you want to do data processing, you can also represent this in terms of these parallel patterns. And so it's a fairly general parallel computation model, right? And so, here's a little more detail showing, the different kinds of parallel patterns. And the key thing about parallel patterns is it tells you both about the parallelism in the computation, but it also tells you about locality, data locality. And those, of course, are the two key things you need for high performance. You need to think about how many things that you can do at the same time in the parallelism, but you also need to think about what data is being accessed, the locality, and keeping that data in a way that you can access it efficiently, right? So then thinking about these domain-specific languages, then they can be represented as hierarchical parallel patterns, right? And so if you're then thinking about compiler flow for these things, then you can take the high-level operations in the domain-specific language, and you can convert them to these hierarchical data flow graph of parallel patterns, right? And then you can optimize these patterns, by improving the parallelism and the locality by tiling and by using an idea called meta pipelining, where you can think about how to execute these hierarchical parallel patterns in a pipeline manner. And so thinking about these hierarchical parallel pipelines, then you can take them and you can execute them on a variety of different architectures. And one of the things that we wanted to look at was sort of how could you execute these on a reconfigurable hardware substrate. And so that was the motivation for a language that we developed called Spatial. And Spatial is a way of representing hierarchical parallel patterns as a set of pipeline data paths, and allows you to think about parallelism at a fairly low level. And it's a language that was originally designed to be a compiler intermediate representation, but it could also be something that a low-level programmer might like to look at when thinking about optimizing parallelism and locality. And so here's a very simple example of doing a tile dot product with Spatial, right? And so those of you who took the tutorial in the morning have kind of seen this, but it's fairly straightforward. It's a two-level reduce, and what you're trying to do then is, and you have an explicit memory hierarchy. The vectors A and B originally exist in the memory, and they are moved tile at a time from the memory to the on-chip SRAM, right? So the tile A and tile B, and this is the explicit movement, right, from some component of vector A, a tile of vector A into tile A, and a component tile of vector B into tile B, and then you do the reduction within the tile, and then the outer reduce is the reduction across the tiles, right? And so you end up with some hardware that looks somewhat like that, right? And so spatial then can be the representation of an accelerator. And so then you think about this hierarchical parallel pattern IR, which is converted into a spatial IR, which can then be mapped to hardware, right? So what kind of hardware would you like to develop to accelerate this style of parallel pattern representation in spatial? Well, we came up with an architecture called plasticine. So this is a reconfigurable data flow architecture because it's meant to execute data flow, but it's reconfigurable, right? So the idea is you're not executing instructions in time, you are executing the instructions in space, and the data is flowing through it, right? So plasticine then can be programmed basically directly from spatial. So if you look at the architecture, it's this checkerboard pattern of pattern compute units in the white blocks and pattern memory units in the blue blocks, right? So you can think about the data being contained within the pattern memory units, and then the data accessing being contained within the PMUs. And this data is accessed and then it is streamed to the pattern compute units, which actually does the computation. Then, of course, communication happens through the on-chip network, which is provided by the switches in yellow. These are the two students who at Stanford developed the ideas initially. What we showed back in 2017 is that if you did something like this, you could get dramatically better performance per watt than a FPGA. And part of the reason, of course, is you don't have the fine grain configuration. It's a much coarser grain of configuration. And then you have a programming model that is meant to map to that, right? So you're not writing Verilog, you're writing this much higher level representation of the algorithm, which, as I just explained, matches very well with what you want to do in a lot of the data processing sorts of domain-specific languages. So we thought this was a really good idea. And, of course, we have to add another layer to our compiler flow, right? So we're going to take the spatial and we create a IR that we call plasticine to match the architecture, and then we've got a low-level compiler to optimize for that, right? So that's work we did a few years ago. More recently, we have some work on thinking about, what if you want an even higher level representation of the algorithm in sparse linear algebra? So working with Fred Kolstad, who's a faculty member at Stanford, and a couple of students, Olivia Sue and Alex, who's in the second row here, thinking about how to take these representations and convert them to reconfigurable data flow, right? And so one of the key elements of this work is taking these high-level tensor languages and converting them into a representation that matches data flow, and it's done through a representation called the sparse abstract machine, and then you can convert that to spatial, and then you can run it on top of an enhanced plasticine that can support sparsity more efficiently, and that's work done by Alex on Capstan, which is a sparse enhancement to plasticine. Okay, all right, so back to the original plasticine and sort of commercializing those ideas, right? So in 2017, we founded a company with Rodrigo Liang, who's the CEO, Chris Ray's another faculty member at Stanford. The company's called Zambinova. It started in 2017. It's now 500 plus people. It's had lots of investment, and it's commercializing these reconfigurable data flow architecture ideas. And the first chip that was developed was called the Cardinal SN10, right? So anybody who knows about Stanford athletics knows that Stanford athletic teams are called Cardinals, so hence the name. And this was, in fact, the first ML chip to be done in TSMC 7 nanometer. So it's a fairly impressive chip. You know, it came out, was taped out in 2019, so it's been out a few years. 40 billion transistors, 320 teraflops, 320 megabytes on chip, and then direct interfaces to terabytes of memory off chip. So, you know, a few slides ago, I said, hey, you want to be able to support huge models, right? So how do you support huge models? You put lots of memory closer to the compute chip. So those of you who know about GPUs know that GPUs have gigabytes of memory, but it's high bandwidth memory. So one of the questions you might be asking is, how do you get away with having DRAM as opposed to high bandwidth memory? How do you actually compute efficiently there? And that's going to be a key question that I'm going to answer in just a moment. But first, let me talk about the architecture in a little more detail, right? So these are ideas, as I said, that originally came from the work at Stanford on plasticine. So this idea of this checkerboard connection of units between the PCU and the PMUs and PCUs. And the PCUs are these SIMD pipelines, which provide the vector and systolic computation capability. The PMUs have this ability to do the decoupled access of the memory, right? And so you've got the ability to access memory in various different ways and supply the bandwidth necessary to keep the PCUs busy. And then you've got this wide vector interconnect provided by the switches and the ability to take computation and unroll it in space and vectorize it and pipeline it so that it uses the computational fabric efficiently, okay? So PCU, as I said, is a pipeline set of SIMD units. The PMU has both the ability to do address generation for the accessing the memory in different ways, and then also a banked set of scratch pads to supply the appropriate bandwidth, right? So the question is, you know, how does this all work together to execute these ML algorithms efficiently? Well, as I said, what you're trying to do is you're going to execute this kernel of this graph of kernels. And so you think about the way that you do this on a conventional accelerator like a GPU or, you know, some enhanced CPU. What happens typically is you do a kernel at a time. So you try and exploit the whole of the computational capability of the GPU on a single matrix multiplier or a single convolution, right? And then once that convolution is done, the data is shipped off to the HBM, and then the next kernel picks the data up from the HBM and does its work and then deposits its results in the HBM. So you have this constant shuffling of data between the GPU device and the HBM, which of course is a huge amount of bandwidth that is required for that. Think about the way that you do this spatially, The way that you want to do it spatially is you lay out the whole of the graph, or as much as the graph as will fit on a single chip. And then of course you can move to separate chips, or you can do things in time too, right? So space is the obvious way to do things, but you can also use time. And now what you do is you allow the communication to happen very efficiently on the network that's on chip between the different kernels, which are executing at the same time. And then, of course, you're going to use pipelining so that, when the earlier kernel is working on a later sample, the kernel downstream is going to be working on a later sample, right? So you see the pipelining showing going on there. So what you get is natural fusion, right? Because the data is staying on chip, and as we all know, the benefits of fusion are that you increase the operational intensity of the whole computation, right? So instead of doing a bunch of memory access, the data stays on chip and flows between the different components on chip. And the net result of that is it looks like you have higher operational intensity than you had before, right? And you can do this without building a custom fused kernel, right? So if you think about how you would do this with CUDA, you'd have to go write a kernel that does the fusion. Here, you naturally get the fusion because you've got both of these kernels executing at the same time. All right, so what this means is you fundamentally think about, you need a different compiler, right? So I've kind of hinted at some of the things that you need in your compiler, but fundamentally you've got to think about a compiler that is trying to look at look at the whole graph and think about how that graph is going to be executed in space and time. So you need a data flow compiler. You don't get to think about things a kernel at a time. You want to think about things, as a data flow graph, and think about how to optimize the communication between the kernels, and think about how much of the resources are going to be taken up by any one kernel, right? Because you can dial up and down the amount of parallelism to match the different components of your pipeline, such that you make sure that everything's balanced. We all know if you're going to pipeline, you need a balanced set of operations, right? So this is, of course, a fundamentally more difficult problem because you now have a global optimization that one needs to do. All right. So how much better can you make this? Well, this is a recent paper from the folks at Google who are thinking about how to improve their TPU, right? And the conclusion they came to is, hey, you want to build something that looks like plasticine, right? So then which you, instead of having these big monolithic matrix multiply units, what you want is a bunch of little units with memory spread around and an interconnection network between them. Looks like plasticine. And so they independently came up with the conclusion that you want to build plasticine. And then they kind of showed what benefits you would get if you did that and you started executing things in data flow. And so what you see in green here is the fusion, right? And they're doing that with their compiler. As I said, dynamically, you can make that work without doing explicit fusion using an architecture like plasticine. And then you also get benefits from better scheduling, which is sort of what computation is executed at any one time. So the red component is better scheduling, the blue is better fusion, and you have both image ML algorithms, efficient net through ResNet, and then you also have the natural language processing benchmarks, the BERTs, and again you see the better data path. Once you have a better data path, then you can exploit that data path with better fusion and scheduling. So there is a significant improvement in doing these sorts of things and building a architecture which looks more like plasticine. Back to this idea of supporting block sparsity. So the paper at ICML, I think, show that, hey, that with these sparse approaches, you could get the same accuracy, you get a speed up a factor of 2 or so. And the question is, how could you do better, right? So one of the key components of these sparse block algorithms is a block diagonal sparse gem, right? So you want to do a gem in which one of the matrices is block sparse. And it turns out what happens is that essentially that will divide the one big gem into lots of little gems, where each of the gems does a stripe of the second matrix, right? So a block of the first matrix over a stripe of the second matrix, and that you put the results of that matrix multiplied together with a concatenation, then you'll have done the complete block diagonal sparse gem. And so you can think about the sparse gem as being a split of the second matrix, a bunch of dense gems, and then a concatenation, right? And so if you're thinking about implementing a sparse transformer with these sorts of ideas, then you're going to focus on the gem components of the sparse transformer. And it turns out that what happens when you make them sparse is that you get, of course, many more of them, many more of these small gems. And what you want to do is you want to execute as many of them in parallel as you can. And having a large on-chip capacity, on-chip memory capacity is useful. And the other thing that's useful is being able to connect them together using data flow and being able to fuse them together. And so it turns out that if you do this, you can execute these sparse blocked matrix computations more efficiently and better than using a GPU. So 3 to 5 times the performance on a sparse transformer. If you think about all the things you need to do, both the gems in the multi-headed attention and the feed-forward network, but also the fusion of the layer norm together. And so ultimately then you get a more efficient way of doing these sparse matrix computations. As I said, one of the key things that you get with these RDU capabilities is a lot more memory, right? But the memory is DRAM, it's not HBM. And the reason that you can get away with DRAM is back to this idea of fusion and keeping a lot of the data communication on chip. And so effectively you've improved the arithmetic intensity of your overall application by having this fusion. And that allows you to have a very, very large memory that has less bandwidth, but enables you to build a machine with much more memory than you can with a GPU, but then still get very high performance because you are doing this fusion. And so you can run large language models, you can do very, very large image recognition models that can get higher accuracy because you can look across the whole image. You don't have to segment the image and think about what happens at the boundaries. You can handle the whole image and you get higher accuracy. And so we've shown a bunch of cases where the accuracy improves because you are running the image recognition algorithms over a larger image. So are we done with the architecture? Have we done all that we need? Well, turns out that you might still want more flexibility than you get with a generic reconfigurable data flow architecture, as I've just described. You might want the capability that you have with more traditionally when you think about GPU running programming with threads. So one of the questions is, can you do irregular data flow with data flow threads, right? So that the idea is, can you beat the GPU at its own threading game? And so this is some work that was done by Matt Willem and Alex. And so what you want to do is to be able to support pointer chasing algorithms, which can be very efficient for some some applications in graph analytics and data processing, and you want to overcome some of the limitations that GPUs have with thread divergence, right? So thread divergence typically happens when you've got a branch and some of the threads go one way, some of the threads go the other way, and the GPU can't execute both of those at the same time. And so it has to serialize that computation and it becomes inefficient, right? And so it turns out that with data flow threads, hey, you can have your cake and eat it, right? You can go both ways, right? I've forgotten which was the guy who said, when you get to a fork in a road, take it, right? So there's an example where you can take it. You can take both sides, and you can execute both of them at full rate. Enables you to do some very sophisticated data structures, which traditionally are difficult to implement on and vector threaded architectures, right? So you can do hash tables and B trees and R trees and all these sorts of things. And so the idea is that, going forward, we can imagine that these ML algorithms are going to become more complex. You're going to have multiple ML algorithms in one big model. These called multimodal models, where you've got different types of models all combined, and you need to decide based on the data what part of the model you're going to use. And so you've got branches and control flow and irregular sparse behavior happening all the time, and you want to be able to run those sorts of algorithms very efficiently. So you think about support for irregular data flow with sparse, irregular data access with sparsity. You also want support for irregular control flow with ideas like data flow threads. So what I hopefully convince you is that this reconfigurable data flow paradigm is pretty general, right? It's not limited to just accelerating these sorts of very basic machine learning algorithms. It could be used for things that are much more general. Okay, so let's switch gears on thinking about sort of, so we have now a way of executing machine learning algorithms very efficiently. We thought about how to do that with better systems. Now let's think about how we might use ML to improve systems, right? And so this is, in fact, the major topic of the workshop. And so what I'm going to say is going to be in line with what some of you have already seen in the workshop, right? So the idea of sort of ML for networking. So the ML algorithms are actively being used to replace the heuristics which people are using to design networks. As I said, I'm not a network expert, and so all the detailed questions should be directed to Shabazz. But as we'll see, some of the ideas that I just told you about will, surface here. Right. So there are all sorts of things you want to do. You want to do load balancing. You want to do packet classification. You want to do resource scheduling. You can use heuristics. These heuristics are kind of limited. They don't handle special cases. They don't adapt to the dynamic environments. And these are all places where machine learning can do better, right? And so the question is, if we can come up with machine learning approaches to these problems, right? Problems that were difficult in natural language processing and image recognition could be solved by these machine learning models. And of course, you see the data, you build the model, you then use that model to make predictions. And so you can imagine that the same thing is true in networking. And so the idea is, okay, let's use these ideas in networking. You say, well, how could I deploy this sort of capability in the networking environment, right? So I could try and do it in the control plane. And so here are some times for running anomaly batch one, so single batch or non-batch anomaly detection on a deep neural network in the control plane, right? So it takes 0.67 milliseconds on a Xeon CPU. The accelerators, because it takes time to get there, take even longer, right? So clearly, these times mean that, there's no way that you can run at line rate. And what's more, you got to send the data over to the control plane just to use any of these devices that sit in the control plane. So clearly kind of doing things in the control plane are not going to be the way in which you can do line rate ML, right? And you say, okay, well, let's think about doing it in the data plane, right? The problem with the data plane is, of course, the data plane as currently construed is optimized for doing the sorts of things that one does in a network, right? So it's match action tables. It's kind of the big innovation in the architecture of switches for networking, right? And they're designed to run these rules very efficiently, but they're not really designed for ML computation, the sort of dense and sparse linear algebra computation that is the core of these algorithms. And so, the VLIW sorts of architectures that are, the core of these pipelines don't work very well. And so you can't do very sophisticated kinds of algorithms. So you're limited to some things that are very, very simple. And so what's the solution? Well, let's enhance the data plane so that we could actually do these sorts of things. And so that's the idea behind Taurus, an intelligent data plane, right? And so what we've done is we've taken the standard pipeline and we've enhanced it with what I'm calling plasticine RT. I think in the Taurus paper, it's actually called a map reduce unit, but you get the idea. So I wanted to make the connection to plasticine, right? So plasticine real time, right? So it's reduced, it's cut down, it's designed for this this very efficient inference capability. But the same idea, you see the checkerboard pattern of pattern compute units and pattern memory units. And the key people behind that, are all in front of us, Tushar, Alex, and main direction comes from Shabazz. And so this paper appeared at ASPLOS this year. And, it was one of the first conferences to actually happen in person in Lausanne. So that was great. And the whole idea is that now you have enhanced the pipeline such that you can handle data, handle ML at line rate, right? So this kind of shows you an example of how things work in the Taurus pipeline. You have packets that come in and potentially you read some local features, the IP address, you get the out-of-network events, you do the inference on the ML model, and you might mark a packet as anomalous, something that you might be some sort of attack, and maybe the result of detecting that some anomalous is that you want to drop it, and so you can do that with the match action tables. We'll kind of apply that rule, and then you can schedule and forward the packets, right? And so in order to investigate this idea, since we didn't have an ASIC built that actually implements this pipeline, we have a Taurus test bed, which is a combination of Intel server, a Tofino switch for implementing some of the P4 match action table capability. And, we couldn't incorporate the Samba Nova chip because it doesn't quite fit into the system that we define. And so the way that we implement the map reduce unit, or the plasticine RT component, is with an FPGA, right? So the FPGA is connected to the Tofino by a 100 gigabit Ethernet link. So this is the Taurus test bed in which we are going to try out some of the ideas of sort of data plane ML, right? And so an example of doing anomaly detection on the Taurus test bed, what we see is that the Taurus line is in blue and the control plane line is in green. And as we increase the sampling rate, the control plane, because of the time it takes, to go from the data plane to the control plane and then instantiate rules and so on, takes too much time. And so the Taurus line keeps up, and the control plane line does not. And if you look at the accuracy of the anomaly detection, right? So the software approach basically falls off a cliff as you increase the sampling rate. Doesn't, start out very high. Whereas the Taurus implementation, detects almost 60% of the anomalous packets, and then the F1 score is considerably better too. So there are lots of advantages to being able to do ML, and the question is, can you do it at line rate? And with Taurus, you can. So that's the whole idea. All right, so great. We can do this sort of capability. And now the question is, how do you make it more accessible to people, in particular network operators who want to use it? So this is the whole idea of declarative machine learning, which is having a real big moment in the machine learning world, which is sort of, in the past, you're really cool if you came up with a new model for, a particular problem that you wanted to solve. But these days, building a model is no longer a big deal. People really want to focus on the problem they want to solve, and they would rather not have to develop new models, right? So foundation models is one approach, right? But, it's not clear that foundation models are the thing that you want in networking. Maybe you do, but I think they're probably at the moment a little big and not quite focused. But you still want this idea of being able to focus on the problem and not have to worry about all of the details of developing the underlying capability to be able to deploy something on something like a Taurus platform. Okay, so there's so many things that one has to do. One has to think about the different components of the system, the P4 for the Tofino, the spatial for the MapReduce component, thinking about how to develop the model itself. What model do you want? What parameters do you want to your model to overarching parameters do you want your model to be focused on? How do you achieve those by tuning hyperparameters and so on? So, you have to become both a machine learning expert, an expert, of course, in networking, an expert in sort of high performance system implementation all at the same time. So this is too much for most, researchers, let alone, I shouldn't say a lowly network operator or not. Network operator is not going to be somebody who has these sorts of capabilities. So how could you do declarative ML for network operators, right? So here you want a high-level directive that expresses the user intent. And so they express what they want, right? So you're going even high. It's a domain-specific language, but maybe it's a domain-specific language for the network operator. So it's very high level. And then you want to automatically come up with a model that meets the user-specified objectives, right? And so this requires some amount of design space exploration, right? And so you want to do that automatically, and then you want to use the constraints to help you do this auto ML process, right? And so the idea then is homunculus, and I thought I had some pictures here. Yeah. Somehow it's dropped out. Anyway, Tushar, Shabazz, and Alex were involved in this, right? So homunculus is this idea of user specifies the data set environment and constraints, and the homunculus system explores the design space, comes up with a model, and uses a optimization environment called Hypermapper to come up with a model that meets the constraints, and then generates the spatial that can and the appropriate P4 is used to drive the Taurus pipeline. So the architecture has a component of the has a interface called alchemy, and the alchemy specifies the data set, the network performance constraints, and target for resources, right? And then so that's the alchemy front, and the optimization core, as I said, is this design space exploration. And then you've got a platform specific backend that could map even potentially from the to something that looks like plasticine, or something that looks like the Taurus testbed, right? And so what you now have is a complete system for exploring these ML models and generating something that can run efficiently at line rate for a variety of different kinds of problems that the network operator wants to solve. Okay, so that's the homunculus. And so over time, of course, we want to continue to raise a level of abstraction at which you can define the problems that you want to solve in networking with ML, and then achieve both performance and efficiency by both developing the right sets of optimization capabilities and potentially changing the underlying architecture, right? So there's more work to be done here. We're just in the early stages of this whole idea of how is ML going to transform networking once you think about these efficient capabilities and primitives that are embedded in the data plane. Okay, so in conclusion then, the virtuous cycle continues, right? So we want, these data flow compilation capabilities combined with data flow architectures are going to give us more efficient systems for ML. This is going to lead to much more accurate, more highly parameterized models, right? For NLP, high resolution images, recommenders, and of course, networks. So you think about data center networks and applying these kinds of system implementation ideas like Taurus that can do data plane inference at line rate. And this will, of course, enhance our capability to develop systems that can be used for improving ML, right? Because at the end of the day, as I said, for these very large models, it is a distributed computation problem, in which the network is going to be a key component, right? So let's think about how to apply ML to improve the systems that we use to develop more ML. And so we're going to get more machine learning, and of course, the cycle continues. So thank you, and I'd be glad to take questions. Yeah.
Just a question on like the energy consumption of this model that short.
Well, it's interesting. So there's a paper that said that these models, training these large models, took a lot more energy than that was claimed, right? So there's sort of a counter paper published by Google saying that the numbers were way off, that they didn't take advantage of kind of very, very coarse grain sparsity that they were exploiting at Google, and that the numbers they had for how much power each of the devices were taking way off. And so I think at the end of the day, the Google claim was they were a couple orders of magnitude too high. And so, how much stock to put into that is unclear, but I can say that the numbers that we have from Zambanova are closer to what Google is saying than what were published in the paper. Other questions?
I think maybe one question I can ask, like, so I know I'm working on this thing with you, but
so you can
like,
ask your own question.
Yeah, there is this thing about the Zambanova system coming in and all that.
Yeah.
I think like, so you mentioned like it's focusing on like ML stuff, but like other computational stuff like that are coming up, like non-ML kind of computation. So these kind of architectures can definitely benefit those environments, and that might be the next direction.
Yeah. No, I think, I mean, there's two things going on, right? One is that there are other parts of the pipeline to creating an ML model that are not dense or sparse linear algebra. There's a data processing component. Now, one could argue that that component, you do it once when you're doing the preparation of the training set, and then most of the time is spent doing the training itself. But there are other kinds of ML algorithms that people are thinking about where data processing is in the core. So you might be doing a database lookup in the core of the training algorithm, right? So then you can imagine that you really care about doing very efficient data processing. And so that's one thing that's happening. Another thing that's happening, if you look at the scientific computation realm, is this whole idea of surrogate model building, right? So here, the idea is you want to simulate climate, or you want to simulate fluid flow over an airplane wing. And, you want to be able to do this at sort of very high fidelity. As you increase the fidelity, of course, the amount of computation you need increases. And so the goal would be, how could I use a machine learning model to approximate the computation? But as the computation proceeds, that model will have to change and adapt. And so what you think about, the way to think about it is that you've got an outer loop of traditional simulation and an inner loop of ML that is being continuously retrained with the outer loop of traditional simulation, right? So you've got both inference and training going on at the same time that you have traditional simulation. So what you really want is the capability to do all those sorts of things in a very close coupled environment. Yeah.
We easily understand why we want to put it there. It's for some of your tasks and I'm not really into this field. I wonder, like, before people are doing this in digital base, like in algorithms, but it's easier to know what to do.
Yeah.
I thought machine learning is typically something that you do for things that you're training in examples and where you don't really know what to do. And so I'm wondering, is there like an intrinsic measure between machine learning and these tasks, or is there something that I'm missing?
I'm going to do some redirection here. Shabazz, what's the answer?
I think in this case, like when you're talking about like knowing and not knowing something, right? So now the environment that we're working in, like cloud data centers and everything, like the traditional notion of like, oh, we know what traffic is coming and what we want to do is not visible to you because the client is actually a tenant, which is hidden from you. So it's very hard to sort of make those. So the bigger the systems are becoming, the bigger the cloud data centers are becoming, it's harder to know what's going on. And this is why we need to sort of need these kind of solutions. So clearly, like when we move from enterprises to cloud and those environments, this sort of knowledge or insight that we had before is sort of like going away. So that's why these kind of models are like ML and these things can help in those environments.
So it suggests adding inference capability to pushing how much inference power you need.
Yeah, that's what again. Yeah,
The problem is how much of the area of the switch has to be to really assist it.
so again, in our paper, we show that the areas. So for example, if you look at other implementations that people have talked about, like for scheduling FIFO and stuff, so they were, and especially in the Conga case, like for adding this sort of a new ASIC chip, like logic in the ASIC, they were consuming around, like the numbers are there in the paper, and they were consuming around 10% of the ratio overhead and stuff. So we did those comparisons, and in our case, for the design that we have proposed in the paper, is around taking like 3% more area overhead, but we have to think of it in a way. You can either add more area on the chip, like to sort of make it bigger, or you can take away some tables. For example, instead of having 54 tables, you can say, okay, I'm willing to give away 3 tables that maybe add to logic that can do this additional capability. So it's like having a new profile. Like we already, like if you go on these websites, these products, they have different profiles for a 32-port switch with 4 pipelines, another switch with 2 pipelines. So similarly, this is another switch which gives you this capability. Now, whether to have that same capability with the biggest beefy system out there, yeah, so again, there is some innovation that is involved there.
I'm not sure it answered my question, but the question is how much power you need. I mean, it can be more efficient than other implementation, but eventually you know what the application you would need to do.
So starting step, so eventually, like more easier to have things will happen. Yeah.
Yeah, I think we don't have a definitive answer yet, but we can certainly see cases where the ML algorithm is better than the current heuristics, right?
Problem is that machine learning inference.
So it's increasing the power
We
of
use the other things that we are doing, and if you will have this which is in the field to get all the data. So if you reduce the, let's say, the performance by half by doing that, then nobody will
Right. Yeah.
deploy it. So you will not get any incoming. You will not be able to kind of see what you can do with it.
Right. So I think you'll take
It sounds something very small, maybe, but then it might not
Might not.
solve the problems that you want.
Yeah.
So I think the idea here is like, again, I'm not sure whether it will answer your question, like by adding these more capabilities in the switch, we are increasing the power footprint of the switch in some way. But it only makes sense if that new capability is taking away power from somewhere else. Like maybe it's taking away an entire rack of system that you were using for doing an omelet selection or like some software. And now this single switch is able to do the entire rack of stuff. So yes, you were able to like sort of bring the power down of the overall data center. But again, these things will eventually, like time will tell how they come out. Yeah.
But for time to tell, you need the capabilities.
Yes, so that's what we're working on.
You are
That's what we're working on. That's what we're working on and trying to add and hopefully have these products.
Yeah.
Question about the whole model fusion approach versus resource segregation. So the way I understand, so the model fusion means you have a big model that cannot fit in memory. So you break it up into smaller models and fuse them together. That's the approach.
Well, the idea is that instead of taking all the resources to execute a single kernel, you put multiple kernels executing at the same time. Now, you might argue that you are not using all the resources. I mean, the speed of each of the kernels may be lower than using all the resources on a single kernel, but what you will get is much more efficient use of the data, right? And so it turns out there's a bunch of overhead that you incur, and many times it turns out that you don't have the right size of data to efficiently use all the resources of a GPU on a single kernel. So much of the resources are not being fully utilized. And so what you're better off doing is, if you could use those resources for another kernel, then you can both, fully utilize the resources, but also get better communication efficiency. And
I'm just kind of trying to compare and contrast the resource memory pooling approach. I have a giant memory using PCI 5, CXL standard. I don't have a memory limitation there. Would there be any that approach that I don't have any memory limitation anymore?
Well, I mean, you got to think about bandwidth latency to that memory, right? Yeah, I mean, if your bandwidth is significantly lower to the CXL memory, then you're not going to get nearly the same performance. Yeah, I mean, if you can get there, if you can get the same bandwidth, fine. But you certainly can't get that today. Yeah.
Thank you. So I have a question for that cycle. The models that benefit the most from improvements in networking, like natural language, image classification, they tend to be very large and to require a lot of resources.
Right.
But on the other hand, if we look in the literature, the models that are used in networks, they are much smaller. Typically, perceptrons are very few layers in a DNN.
Yeah.
So where do you think the overlap is for now, or maybe where it will be in the future?
Well, I mean, I think that in fact, if you look at where you get the biggest bang for the buck in this fusion-based approach, it is for these small models. That's where you get the 10x improvement. So the idea of sort of how to execute these models efficiently using this spatial approach is something that can be used quite effectively on small models.
Any other questions? All right, I think let's thank the speaker.
Good.